Hey everyone, before we jump in, if you're getting value from these explainers, please take a moment to subscribe, hit that like button, and share it with your friends. Okay, so CAR T cell therapy. It's been a massive success story for blood cancers, right? And we're even seeing some really inspiring data in autoimmune diseases. But today, we're diving into a much tougher problem, these solid tumors. And this isn't some small niche problem. We're talking about the vast majority of cancers. Solid tumors, lung, breast, colon cancer, they make up about 90% of all human cancers. So cracking this code, it's one of the biggest, if not the biggest, challenges in medicine today. All right, so here's our game plan for today. First, we'll dig into the solid tumor challenge itself. Then we'll look at how we're adapting the attack with T cells. After that, we'll explore a new wave of therapies using innate cells. We'll put them head-to-head to see how to choose the right therapy. And finally, we'll look to the future, which is all about a combined assault.
Okay, let's start with Section 1, the solid tumor challenge. The big question is, why are they so difficult to treat? So why is a solid tumor so incredibly hard to crack? I mean, the amazing success we've seen with therapies like CAR-T and blood cancers, it just doesn't translate here. And that's because solid tumors are, for all intents and purposes, biological fortresses. They have these powerful, active defenses designed to keep attackers out.
It really all boils down to three major roadblocks for CAR-T. First up is what's called antigen heterogeneity. Basically, the tumor cells are a chaotic mess. They don't wear a consistent uniform or antigen that our cell therapies can easily lock onto. Second, there's the immunosuppressive microenvironment. This means the tumor is actively fighting back, creating a hostile zone for any immune cells that get close. And third, even if our engineered cells manage to get there, they struggle with poor infiltration and persistence. They just have a really tough time physically breaking into the tumor and then surviving long enough to actually do their job.
And that second point brings us to this absolutely critical concept, the tumor microenvironment, or TME. You have to think of it as this complex ecosystem that the tumor builds around itself. It's like an active battlefield, and the tumor is the commander. It recruits all these inhibitory cells like TREGs and MDSCs and has them send out signals that just turn off our attacking T cells. It leads to what we call exhaustion, basically creating this protective shield that makes our best soldiers totally ineffective.
All right, Section 2, adapting the attack with T cells. Now we're talking about evolving our therapies to see more targets. So, to break through these defenses, the first logical strategy is to make our star players, the T cells, even smarter and more powerful. We need to evolve them so they can see a much wider range of targets. And this slide really gets to the heart of a major evolution in T cell therapy. Your standard CAR T cell can only see targets, or antigens, that are sitting right on the surface of a cancer cell. But tcr-t technology is different. It can recognize tiny fragments of proteins from inside the cell that get presented on the surface. Think of it this way. CAR-T is like a security guard who can only see who's standing outside the building. tcr-t is like a guard who can see what's inside their briefcase. It's a whole new level of detection. And what this does is just blow the doors wide open on the number of potential targets. I mean, we go from being limited to that small handful of proteins on the cell surface to being able to go after targets from something like 90% of all the proteins inside the cell. This is a potential game changer, especially for tumors that are really good at hiding their identifying markers on the outside. But, it's not just about the weapon system, it's also about the composition of the army. We've learned that having the right mix of soldiers is absolutely critical. What the research is showing now is that CD4 plus helper T cells aren't just helpers. In solid tumors, they're powerful killers in their own right, and they stick around for a lot longer. So the new consensus, the new gold standard, is to use a very specific 1-to-1 ratio of these CD4 plus cells and the CD8 plus killer T cells. It gives you the best of both worlds, that immediate firepower combined with long-term survival. Okay, moving on to Section 3, a new wave, innate cells. We're talking about off-the-shelf therapies that can recruit the body's own defenses. But, just upgrading our T cells isn't the only play here. There's a whole new wave of therapies coming through that leverages a totally different part of our immune system, our innate cells. These are the body's first responders, and they can be engineered into these incredibly powerful, off-the-shelf treatments that are ready to go. A perfect example is cARNK cells. Now, they do attack the tumor directly, sure, but their real magic is that they act like kindling to start a much bigger fire. They recruit and activate the patient's own immune system, specifically dendritic cells. This kicks off this broad, long-lasting attack against a bunch of different tumor antigens, And that attack keeps going even after the initial CAR-NKT cells are long gone. Then you've got another really clever approach using CAR gamma delta T cells. These things are the ultimate multitaskers of the immune world. First, they're natural-born killers, so they attack cancer cells directly. But at the same time, they act as a living vaccine. They actually pick up pieces of the dead tumor cells and present them to the rest of the immune system, basically training other T cells on what to look for and destroy. All right, Section 4, choosing the right therapy. Let's do a head-to-head comparison of these key attributes. So now we've got these two big strategies on the table, upgrading our adaptive T cells and weaponizing our innate cells. So let's put them side by side. Let's really compare them on the practical things that matter most for patients and doctors. So the big question is, how do these different therapies really stack up when you look at things like cost, how long it takes to make them, and how long they actually stick around in the body? And this table lays out the trade-offs really clearly. On one side, you have the T-cell therapies, CAR-T and tcr-t. They're autologous, which is a fancy way of saying they're custom-made from the patient's own cells. The huge upside is high persistence. They can last for months, sometimes even years. The downside, they're very expensive and slow to produce. We're talking 2 to 6 weeks. On the other side, you have the innate cell therapies. These are allogeneic, meaning they can be made from healthy donor cells and stored ready to go off the shelf. This makes them way faster and cheaper. The trade-off is they have shorter persistence, only days or weeks. But remember, as we just saw, some of them are designed to kickstart the patient's own long-term immune memory, which is a really neat trick. And that brings us to our final section, the future, a combined assault. Because victory here is going to require a multi-pronged strategy. So what all this really tells us is that there's no single silver bullet. There's no one-size-fits-all solution. Each of these approaches has its own unique strengths and weaknesses. The future of conquering solid tumors, it seems, isn't about picking one winner. It's about combining these powerful tools into a coordinated, multi-pronged assault. And that combined assault has to start before the cell therapy even gets there. The first step is to remodel that hostile tumor microenvironment we talked about. We can use drugs like checkpoint inhibitors, you might have heard of anti-CTLA4 or anti-PD1, to clear out the tumor's bodyguard cells and weaken its defenses. There are even other drugs like CSF1R inhibitors that can stop the tumor from recruiting more of these suppressive cells in the first place, and even reprogram them to be anti-tumor. It's like dismantling the fortress's shield before you send in the troops. And this all leads us to a potential 3-step strategy for the future, a master plan for achieving lasting remission. Step 1, remodel the TME. Use those checkpoint inhibitors and other drugs to make the tumor vulnerable. Step 2, deploy the cell therapy. Send in your engineered cells, your CAR-T, your CAR-iNKT, whatever is best for that tumor, for the main attack. And then crucially, step 3, prevent recurrence. You follow up with something like a DC vaccine, which acts as a long-term surveillance system, creating a lasting immune memory to hunt down and eliminate any cancer cells that dare to come back. And this brings us to our final, and I think very hopeful question. With these new alliances, by combining these incredible strategies, preparing the battlefield, launching a powerful and precise attack, and then setting up long-term surveillance, are we finally entering an era where a patient's own immune system, supercharged and expertly guided, can achieve a lasting, decisive victory over the fortress of the solid tumor?